In this video, we'll discuss the stack and queue data structures. Now, these are important data structures, not only because they're useful in themselves as data structures, but they also provide the foundation for other data structure and algorithm techniques, such as depth-first search and the breadth-first search methods that are seen in tree or graph traversal algorithms.
What is a stack? A stack is a data structure that we're all familiar with from our everyday lives. Consider a stack of books. So here I start with an empty table and I place a book on the table. Then I add another book to the table on top of the stack. And then let's say I push another book to the top of the stack. If I want to select a certain book, I'll take the top book off the stack. So let's say I want to get this book here. I would need to take the top book off the stack and pop that off. It's also known as a pop operation. And as you can see, the last book that I placed on top of the stack is also the first book to be popped from the stack. So just to see that again, the last book, when I placed it there, will be the first one to be removed. So this observation introduces the notion of what is known as last in, first out, or LIFO. This means that we restrict an array such that we can't immediately access an element in the middle of our stack. Consider the core stack. When we call a function from within a function, so let's just say we have some function here, and to simplify, I'm just going to say fn foo. So when we call that function here, well, actually we're defining what it is first. So let's say that it calls another function, which is also defined somewhere else, and that's a bar function. And then it does something else. It doesn't really matter what that is. We just got a comment there. What happens is, well, when our program tries to read this foo function, so let's say that's called somewhere down here. Basically what happens is initially there's nothing on the stack. So I'm just going to do this to the right here to distinguish it from the book example on the left. So on the right here on the table, we have the core stack, and you may see this in the browser. And essentially what we first do is we call the function foo here. So we add the foo to the stack. So I'm just going to put an F here. And then if we look inside of the foo function, we notice that it calls bar. So then we go ahead and we put bar to the top of the stack. And the reason the stack data structure works for the core stack is because when we're executing our code, when our program is being executed, it runs sort of line by line. But if a function's called, it executes those lines in the function first. So this reference to foo is the first function that's being called, but then foo calls bar. So then it points towards all of the lines of code in the bar. And then only after that, all those lines have been executed, then the bar function, those lines of code, they get popped from the stack. So we're left with our foo, and then it completes some operation here, which I've just got some comments. And then only after that's complete will we pop that from the stack to get an empty stack. So you may be familiar with the website Stack Overflow, which got its name from the idea that if you have a recursive function, or if you have recursive function calls that don't get resolved, this will continually push to the stack until you run out of RAM. So the main benefit of a stack over an array is if you only need to insert and delete elements from the top of the stack or the last element, because these are both O of 1 operations. What is a queue? So a queue is an easy data structure to conceptualize because in our everyday life we encounter queues all the time. So let's say we're at a shopping center and we want to buy our groceries, and we go to a checkout, which I'm going to have a stick figure behind a desk here to represent. And then let's say a customer comes. Well, the customer will go to the person, and if there's no one else there, they'll be served. However, let's say that there's more than one customer. Usually what people do is they wait behind the person that was there first, and they have essentially created a queue. And then if another person comes, they'll join the queue. So queues tend to be implemented with linked lists, and the queue, it adheres to the first in, first out sort of policy. So we can see that this first person here, he was the first person to line up, so he's going to be the first person served. So this is also known as FIFO, first in, first out. This is in contrast to the stack, where it was the last in, first out principle. When you join the queue, that's known as being an in-queue method. And once you leave the queue, when this guy finishes or a task gets run, this guy will be dequeued. As mentioned before, queues, they tend to be implemented with linked lists, and that sort of makes sense because you sort of have this dependency on the person next to you sort of thing. So we're going to explore linked lists in the next video. So the stack and the queue, they tend to build up on the array data structure by providing an interface for common methods such as push and pop for the stack, or enqueue and dequeue for the queue. They also restrict some of the built-in array methods, because if they're needed, you'd simply just use an array. And in restricting the data structure's operations, we can improve the time complexity, because as we saw in the case of the stack popping and pushing from the stack, that's O of 1. And this is also true for enqueuing and dequeuing. So if it's possible to use a subset of the array operations and they adhere to either the stack or the queue protocols, they can be more efficient if you're able to solve your problem like that. So let's go ahead and dive into a couple of algorithm questions. Let's dive into some stack algorithm questions first, as we'll see the queue data structure be used in conjunction with other algorithms.